Chapter 14 begins with multiple integration. This section is on iterated integrals and area in the plane. Our objectives are to evaluate an iterated integral and use an iterated integral to find the area of a plane region. Here's an example of a definite integral where we have the integral from 1 to x of the quantity 2x squared y to the negative 2 plus 2y dy. In this example, we're going to be integrating with respect to y. The differential on the outside here is dy. That means you're going to treat the y as the variable and treat x as a constant, and you're going to find the antiderivative. When you take the antiderivative of the first term here, 2x squared y to the negative 2, you're going to add 1 to the exponent and divide by the new exponent. That's our power rule for integration. And the same thing here, you're going to add 1 to the exponent, y2, y to the second power, and then divide by 2. So what that looks like when you integrate, we get negative 2x squared over y plus y squared, and we evaluate that at our bounds of integration from 1 to x. Since this differential was in terms of y dy, we're going to replace the y in the antiderivative with what the bounds are. So you're going to replace, for the upper bound, you're going to replace y with x, plug in x into both of those, and then you're going to plug in y equals 1 when you evaluate the lower bound. And using the fundamental theorem of calculus, you're going to subtract those. So again, we put y equals x in for the upper bound, y equals 1 in for the lower bound, and then when you simplify this, you get the quantity 3x squared minus 2x minus 1. So that entire integral, when you're integrating with respect to y, you get this expression, 3x squared minus 2x minus 1. Now we're going to put that together to create this iterated integral. You see this double integration. You have an integral from 1 to 2 of the integral from 1 to x of this quantity dy dx. We have already evaluated the inside integral. The inside differential was dy, so we integrated with respect to y and plugged in the upper and lower bounds into the y variable. When we did that, we found the quantity 3x squared minus 2x minus 1. So we replaced the whole inside integral with what it simplifies to get the integral from 1 to 2 of this quantity. Now we treat it just like a single integral and take the antiderivative to get x to the third minus x squared minus x, and we're going to evaluate it at the bounds from 1 to 2. First, plug in x equals 2, then plug in x equals 1, and simplify the result to get the quantity 3. This is an example of an iterated integral, and the order of the differentials does make a big difference on how you evaluate this. So in this case, the inside differential was dy. You integrate with respect to y, and then plug in the bounds where the y is. And then when you simplify that, you integrate with respect to x. Now this slide shows you the two orders of the differentials for dy dx. In this example on the left here, we have the integral from a to b of the integral of g1 of x to g2 of x of f of xy dy dx. The inside integral here is the dy. You would integrate first with respect to y, plug the bounds into the y's, and then integrate with respect to x. On the top right side of the screen here, we have the integral from c to d of the integral of h1 of y to h2 of y of f of xy dx dy. The order of the differentials dx dy, you first do the inside integral with respect to x, treat x as a variable and y as a constant, and then you would plug in the bounds in for x. And then once you simplify that, you simplify it to a single integral and you integrate with respect to y. Now the inside limits of integration can be variable with respect to the outer variable of integration. So what that means is the outside variable of integration is x, the outside differential is dx. So you can have x's on the inside bounds. Over here on the right, the outside differential is dy, so you could have y's in the inside bounds of integration. However, the outside limits of integration must be constant with respect to both of those variables. So this is our differential dy and dx. It can't have any y's or x's in our bounds of integration of the outside. Again, on the right, dx dy, you can't have any x's or y's. It must be constant with respect to those for the outside limits of integration. In this example, the outside limits indicate that x lies in the interval from 1 to 2, and that the inside limits indicate that the y lies in the interval from 1 to x. So this over here on the bottom right part of the screen is the iterated integral. The outside bounds is from 1 to 2. The inside bounds is from 1 to x of f of xy dy dx. You look at the outside differential is dx. So that means our bounds for x, the outside bounds are from x equals 1 to x equals 2. And that's how we end up with this interval for x. The inside bounds are in terms of y. Your inside differential is dy, so your y equals 1 and y equals x. Those determine your interval for y. And together those two intervals determine the region of integration R of the iterated integral. And I'd like to look at this graphically, that these bounds will depict a region in the plane, in the xy plane. So if you're looking at the interval for x, the outside bounds are from 1 to 2. We have x is from 1 to 2. The inside bounds are from 1 to x, so y is between 1 and x. When you're looking at the graph, I like to think of the words left and right for your x bounds, bottom and top, or low and high for your y bounds. Your x's, the left x over here of the region is 1, the right x of the region over here is 2. The lowest y value of the region here is y equals 1. The highest y value, well, that depends on the line y equals x. So the left to the right, the bottom to the top, or the left to the right for x, the low to the high for the y.